Hi, good morning everyone. Welcome back to series of lectures on digital logic design. We are discussing unit 2, that is logic gates and gate level minimization, and now we are in session 3. In session 1 and 2 we have discussed some topics. I am going to revise those topics now. Next I am going to continue with this with the contents of this session. First of all, in session 1 we discussed about need of digital logic design. What is the objective of digital logic design and what is the need of digital logic design. Then what are the applications of digital electronics, and then we mainly focused on binary variables and logic operations. Binary variables, what is binary variable and how many forms are there? A binary variable contains only 2 forms, either it is on or off. Okay. And the logic operations, what are logic operations? We have 3 logic operations, and, or and not. We discussed in detail about those 3 logic operations. Next we discussed about logic gates, basic logic gates, and or not, universal logic gates, NAND and NOR, and other logic gates, XOR and XNOR, we discussed in detail. And after that we discussed logic diagrams, truth tables and Boolean expressions in session 1. How to draw logic diagrams for a Boolean expression, how to realize a truth table for the Boolean expressions, and from truth table how to derive Boolean expressions, and from logic diagram how to derive Boolean expressions, we discussed in detail in session 1. And in session 2 we discussed about algebraic manipulation. The algebraic manipulation means simplification of Boolean expressions by using Boolean algebraic laws. We have some Boolean algebraic laws. By applying those Boolean algebraic laws, we are able to simplify the Boolean expression. What is the use of the simplification of Boolean expressions? If the Boolean expression is simplified, then the development of designing of logic circuit is very easy. We can design that logic diagram, logic circuit. And next we discussed about complement of a function. How to find complement of a function? There are 2 ways to find the complement of a function. One is straight away applying De Morgan's laws, we can get the complement of a function. And another way is first we find the dual of a function, then finding the complements of each variable, it gives complement of a function. After that we discussed about canonical and standard forms. What are canonical forms? There are 2 forms in canonical. One is sum of min terms and another one is product of max terms. And standard forms, there are 2 standard forms. Those are sum of products form and product of sums form. And last we discussed how to convert from one canonical form to another canonical form. These are the things we discussed in session 1 and 2. Now we are going to discuss about gate level minimization. Our main focus is gate level minimization only. For that we have already used Boolean algebraic expression to simplify the circuit. Now another method is map method. The map method we are going to discuss in detail. After this map method we are going to discuss, in that map method only we are going to discuss product of sum simplification and don't care conditions, and finally we are going to discuss about NAND and NOR implementation. Now gate level minimization, we know gate level minimization means simplification of digital circuit. Simplifying, how to simplify the digital circuit? By applying map method. See, this gate level minimization is the design task of finding an optimal gate level implementation of the Boolean functions describing a digital circuit. Here we have one digital circuit. How many gates are there in the digital circuit? One is 2 NOT gates, 2 AND gates and 1 OR gate. How many gates total? 5 gates. For the same circuit, for the same output, by using a simple circuit also, we can get the result. That is simplification of this Boolean expression. By using only XOR gate, we are able to get the same output. So, that circuit is simplified like that. This is how we are going to simplify those circuits, we are going to discuss. Here, in this gate level minimization, simplification, this is simplification of Boolean functions leads to simpler digital circuit. Why? What is the need of simplification of Boolean functions? Simpler digital circuit. Simpler digital circuits automatically works fastly. And another advantage is simplification of Boolean functions using identities previously by applying Boolean algebraic class is a time consuming and error prone. And this we are going to discuss in detail about reducing the systematic method for reducing Boolean expressions. See, we are going to discuss about this map method developed by Carnage. That in 1953, Maurice Carnage invented a graphical way of visualizing and simplifying Boolean expressions. This graphical representation known as K-map, Carnage map, is named in his honor. Map method developed by Carnage. So, we are considering it as Carnage map, K-map. So, he is Maurice Carnage. Now, these Carnage maps provide an alternate way of simplifying logic circuit. We know. Already we have one method, that is simplification of Boolean expression by applying Boolean algebraic laws. And another method, this is alternative method to simplify logic circuit, right. Instead of using this Boolean algebra simplification techniques, we can transfer logic values from Boolean statement or from truth table into a Carnage map, and this map is the pictorial form of a truth table, right. And what is the advantage of this? The simplified expressions are produced by using K-map method. The simplified expressions, which form? Either SOP form or PYS form. The smallest expression and the simplified expression is not unique. And the simplest algebraic expression means, what is simplest algebraic expression? Reduction of number of terms or number of literals? Both. The minimum number of terms means minimum number of gates, minimum number of logic gates. And smallest number of literals in each term means less inputs to gates. This is about this is the advantages of this is the meaning of simplest algebraic expression. Now, we are going to discuss about in detail about K-map. First, we are considering two variable K-map. A K-map is a diagram made up of squares with each square representing one minterm of the function to be minimized. Now, the adjacent minterms are combined to form simpler term. How to simplify? Anyway, squares are there. We are representing our minterms in that squares. Then, how to get minimum expression? By combining adjacent squares. This is very important. By combining adjacent squares, we can get the minimized expression. So, here, this is a two variable K-map. How many squares will be there? 2 variable means 2 square. 3 variable means 2 cube. 4 variable means 2 to the power of 4, that is 16 squares will be there. This is 2 variable K-map. We have 4 squares. What are the names of those 4 squares? M0, M1, M2, M3, right. So, what are the values of those? M0 means what? X bar, Y bar. M1 means X bar, Y. M2 means X, Y bar, and M3 means X, Y. This is. And here, the left side row represents the values of x, either 0 or 1, and the top columns represent y, 0, 1. Here 0, 0 means first row, first column, 0, 1 means first row, second column, and 1, 0 means second row, first column, and 1, 1 means second row, second column. Now, this is a two variable truth table. The f of xy is equal to x plus y, just by OR gate. This is simple OR gate only. F of xy is equal to x plus y, simple OR gate only. What is the truth table for this? Xy, that is two variables are there, xy and x plus y. 0, 0 is equal 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1. What is the expression for this? Boolean expression for this. Simplified expression is x plus y. How we are getting that simplified expression? Now we are going to discuss. According to the truth table, what is the Boolean expression? The Boolean expression is x bar y plus x bar y plus xy bar plus xy. So, see how to simplify this one. Okay, we have mapped once, how to group and how to simplify. So, this is we have mapped once, and how to group this one? This is first group and this is second group. Okay, and see what is the simplified expression now? Here the simplified expression is for first group 1, 0, that is xy bar and xy. Xy bar and xy. In this, x is the common term, and in that second group, that is x, that is second one, that is x bar y and xy. In this x bar y, xy, what is the common term? Y. So, we have two terms now, x plus y, that is equal to, that is simplification of Boolean function. Yes, from this we can get x plus y. Now, what are the rules to simplify a Boolean expression by using map method? The rules are, groupings can contain only ones, no zeros. That means we are mapping ones now. Grouping only, we have to group only ones, not zeros. Okay, that is first rule. And second one is, groups can be formed only at right angles, rectangles, okay, squares is possible, and diagonal groups are not allowed. Diagonal groups are not allowed. And another one is, the number of ones in a group must be a power of 2. 2 we can group, 4 we can group, 8 we can group, if it is 16 we can group. So, even if it contains a single one also, not possible. Now, next one is, the groups must be made as large as possible. That is, if it is possible, we have to group 4. Okay, if it is possible, we have to group 8. Maximum, the groups must be made as large as possible. And groups can overlap and wrap around the sides of the K-map also. These are the rules for the simplification of Boolean expressions by using K-map. Now, example. Now, we are going to discuss about 3 variable K-map. 3 variable K-map means how many squares will be there? 2 cube, 8. 8 squares will be there. There are 8 squares means 8 minterms. There are 8 minterms for 3 variables. So, there are 8 squares. These minterms are arranged not in a binary sequence, but in sequence, the sequence is similar to gray code. That means, have a look at this one. Here, x, the values of x, the value of x is 0, 1. First row means x value 0, second row means x value 1. And in columns, 0, 0 is there, 0, 1 is there, fine. after 0 1 we are getting 1 1, okay, after 1 0 is there. So this minterms are arranged not in a binary sequence, but the sequence is similar to gray code. This is gray code only. What is the, why we are considering after 0 1 1 1, there should be change in only one bit. That's why we have considered this one. So that is the rule of K map only. So now this is 3 variable K map. Here 0 0, 0 1, 1 1 and 1 0. The sequence varies like this: x bar y bar z, x bar y bar z, x bar y z, and then x bar y bar z. Okay. Then, we will represent this as numbers, that is 0, 1, 3, 2, 4, 5, 7, 6. This is the minterms. Thus, the first row of the K map contains all minterms where x has a value 0, and the first column contains all minterms where y and z both have a value 0. Now, consider this expression: f of x y z is equal to, f of x y z is equal to, how many variables are there? 3 variables. How many minterms mentioned? X bar y bar z plus x bar y z plus x y bar z plus x y z. This is the expression. And what is the largest group of ones? That is a power of 2. So what is this is the mapping of ones. First, x bar y bar z 0 0 1. 0 0 1 means that is. And second one is x bar y z, represented in first row, third number. And next one, x y bar z. X1 means next row, second row, second column, that is x y bar z, and x y z means see row, second row, third column, that is. And how to group the elements? 4 grouping is possible, then we can directly group 4 grouping, that is 4 grouping is possible. Now what is the simplified expression for this? The simplified expression is, how to get simplified expression? First one, x bar y bar z, right? You write that one. Next, x bar y z, next variable is x bar y z, that is first row, third column. And next one is x y bar z, and the next one is x y z. Among all these 4, what is the common term? Common term is z only, and that is the simplified expression. In our original expression, how many minterms are there? 4 minterms, but we are getting only 1. That is the simplification of Boolean expressions, simplification of logic circuits. Now, this is another expression. How many minterms are there in this? 6 minterms. F of x y z is equal to x bar y bar z bar plus x bar y bar z, this is, and plus x bar y z plus x bar y z bar plus x y bar z bar plus x y z bar. And in this, how to map ones? This is mapping of ones. First one is x bar y bar z, that is first row, first column is 1. Like that we have mapped. And how to group the elements? Is 4 grouping is possible? Yes, 4 grouping is possible. We have, see, this is the two 4 groupings are possible. So how to find the simplified expression for this? We have to find the simplified expression for one group, and we have to see this grouping wrapping. Okay, this possible, and the simplified expression f of x y z is equal to x bar plus z bar. This is green grouping and this another grouping. With these 2 groupings, x bar plus z bar is the reduced function for this, right? And how many minterms are there overall? 6 minterms. From this, see, we are getting only 2 terms, that is x bar plus z bar. This is the simplified expression. Now, another one. See, now consider another expression. F of x y z is equal to sigma 2 3 4 5. Here how many min terms are there? 4 min terms. M2, M3, M4, M5. So, M2, map M2, next M3, next M4, M5. See, what is the simplified expression? So, what is grouping? How grouping is possible? M2 and M3 one group, and M4, M5 another group, M4, M5 another group, right. Now, M3 x bar yz, M2 x bar y z bar. What is the common term in this? X bar y. For M4 and M5, x y bar z bar, M5 x y bar z. What is the common term? X y bar. So, what is the simplified expression for this? The simplified expression is f of x y z is equal to x bar y plus x y bar. This is the simplified expression for this 3 variable K map. Now, we consider another example. Here f of x y z is equal to sigma 0, 2, 4, 5, 6. 0, 2, 4, 5, 6. How many min terms are there? 5 min terms. So, this is the K map. 5 values are mapped. Now, grouping. Which grouping is possible? With wrapping, 4 grouping is possible and 2 grouping is possible. Now, what is the simplified expression for this? F of x y z is equal to x y bar, that is the 1 mapping, 2 grouping, 2 variable grouping, and for 4 grouping z bar is the finalized expression. So, the expression is f of x y z is equal to z bar plus x y bar. This is the finalized expression for this. And next, the another expression is, okay, consider the Boolean function f is equal to a bar c plus a bar b plus a b bar c plus b c. Now, we have to first we have to express this into sum of min terms. Sum of min term means f of ABC is equal to sigma 1, 2, 3, 5, 7. 1, 2, 3, 5, 7. So, how to find minimal expression for this? So, what is the K map for this? How many terms are there? 1, 2, 3, 4, 5. 5 min terms. So, 5 min terms are mapped, okay, like this, and grouping, 4 grouping is possible and 2 grouping is possible. And what is the simplified expression for this? From 4 grouping we are getting C, and for 2 grouping we are getting A bar. So, the finalized expression is F is equal to C plus A bar B, that is. And next one is, this is K map simplification using 4 variable. Till now we discussed 2 variable K map and 3 variable K map. See, now we are going to discuss 4 variable K map. Suppose 4 variable K map means how many squares will be there? 16. For 2 variable K map, 2 square, 4 squares, and for 3 variable K map, 2 cube, that is 8 squares, and for 4 variable K map, 16 squares will be there. So, now we are going to discuss in detail about how to minimize the Boolean functions by using 4 variable K map. Here 4 variables are there. You consider those 4 variables are W, X, Y, Z. Wx are written in left side and vertically, and Yz are written horizontally. So, first row first column means 0 0, means all zeros, W bar, X bar, Y bar, Z bar, that is 4 variable K map first term. And what is the last term? 1 0 1 0, that is 10. W, X bar, Y, Z bar. This is 4 variable K map. And how to write min terms for this? First one is M0, M1, M3, M2, M4, M5, M7, M6, next last row, M8, M9, M11, M10, and third row first column, 12, 13, 15, 14, that is, those are the min terms. Now, see this one. we have populated the K map shown below with the non-zero minterms from the function. The function is f of w, x, y, z. That is equal to, one expression is given, we have mapped the values. That is, first one is w bar, x bar, y bar, z means 1. Next one is w bar, x bar, y bar, z means next one. Like that we have mapped. So, how to group these? How to group all these? There are so many alternative approaches for this. First, how to group this one? First way is, this is. Okay, first way is, 4 corners, 4 values are there. That is one group. So, this is first that pink color represents, that is the purple. There are 3 groups for this. A purple group entirely within the K map at the right. Okay, that is purple group within the K map. And the pink group that wraps the top and bottom. Pink group. And the green group that spans the 4 corners. These 4 groupings are possible, and based on these 4 groupings, we can get the minimized expression, minimal expression, that is equal to w bar y bar plus x bar z bar plus w bar y z bar. This is 4 variable, simplification of 4 variable K map. Now, another, is it possible? It is possible to have a choice as to how to pick groups within K map while keeping the groups as large as possible. The different functions that results from the groupings below are logically equivalent. And it is possible, okay, this is, if these types of groupings are there, okay, grouping here, vertical grouping is possible, horizontal grouping is possible. There are so many approaches for this grouping. And these are the 2 examples. Now, simplify this expression. Simplify f of x, w, x, y, z is equal to, now this is 4 variable K map. How many minterms are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 minterms are there. So, how to map? You know, see here these minterms are M0, M1, M3, M2, M4, M5, M7, M6, M12, M13, M15, M14 and M8, 9, 11, 10. These are the minterm values. So, now 0 we have mapped. How many groupings are there? 8 grouping is possible. 4 groupings are possible. And what is the minimized expression for this? For 8 grouping, okay, we will get y bar. For first 4 grouping, we will get w bar, z bar, and second 4 grouping, we will get x, z bar. Okay, this is now this is another expression. Yeah, simplify f is equal to, we have to convert this into sum of minterms. F is equal to a bar, b bar, c bar plus b bar, c, d bar plus a bar b, c d bar plus a b bar, c bar by using truth table. Okay, suppose in the first one d term is missing. D term is missing means we have to add d bar. That is, for that first a bar, b bar, c bar, d one term and a bar, b bar, c bar, d bar is another term, like that. Second one, a is missed, we have to add first a, b bar, c, d bar, and another one is a bar, b bar, c, d bar. After simplification, we will get sum of minterms. Based on that sum of minterms, we have to group the ones in K map. After that, after grouping, we will get the simplified expression, and the simplified expression is f is equal to b bar, d bar plus b bar, c bar plus a bar, c, d bar. This is the finalized prime implicant and the essential prime implicant in K maps. In K map, a product term obtained by combining the maximum possible number of adjacent squares is called a prime implicant. In this example, the maximum possible number of adjacent square, a product term obtained by combining the maximum possible number of adjacent squares are CD, B bar C, AD and AB bar. And another definition for prime implicant is the bunch of ones on the K map which form a 2 square, a 4 square, etc. is called prime implicant. Again, what is prime implicant? The bunch of ones on the K map, either it is 2 square, 4 square or 8 square. The bunch of ones on the K map which form a 2 square, a 4 square is called prime implicant. Here, what are prime implicants? There are 4 prime implicants in this. AB bar is the last adjacent ones having last row, and this CD belongs to 1 1. Like that, we have 4 prime implicants. And another one is essential prime implicant. What is this essential prime implicant? If a minterm is covered by only one prime implicant, that prime implicant is called as essential prime implicant. Now, another definition is the prime implicant which contains at least one which cannot be covered by another prime implicant is called essential prime implicant. In the previous, this is same example. In this example, what are various, what are prime implicants and what are essential prime implicants? There are so many prime implicants, and the essential prime implicants are BD and B bar D bar. BD belongs to 4 ones in the middle, and B bar D bar related to all 4 corners. These are called essential prime implicant. Again, if a minterm is covered by only one prime implicant, that prime implicant is called essential prime implicant. For this diagram, the essential prime implicants are BD and B bar D bar, all middle and all 4 corners. These are called essential prime implicants. Now we have discussed about 2 variable K map, 3 variable K map and 4 variable K map. Now this is 5 variable K map. See, 5 variable K map contains how many number of squares? 2 to the power of 5. 5 variable K map means 2 to the power of 5. That is, it contains 32 squares. These 32 squares are represented like this, and it varies. Like first one is like our 4 variable K map: M0, M1, M2, M3, M2, M4, M5, M7, M6, M12, M13, M15, M14, M8, M9, M11 and M10. And the second, that is first 16 is this one, and second 16 is another one. In first 16, A value is 0 and another second 16, A value is 1. If the values of if the variables are A, B, C, D, E, A, B, C, D, E, the row represents BC and the columns represent DE, and the entire first square, table, that represents A is equal to 0, and second 16 minterms represents A is equal to 1. This is a 5 variable K map. And now we are going to discuss in detail about product of sum simplification. Till now we have completed sum of product simplification. Now what is product of sum simplification? For product, there are these are the steps to get product of sum simplification. Mark the empty squares by zeros. Till now, for any expression, if a Boolean expression is there, or f of xyz is equal to sigma 0, 2, 3, 4, 5. This is our Boolean expression. In that, for 0, 2, 3, 4, 5, what we are doing? We are mapping ones in that K map. So, what we have to do now? Mark, already we marked once. For the remaining empty squares, you fill with zeros. Then combine them. We have to combine. That means by grouping we can get f complement. We obtain f complement, the complement of the function. Take the complement of that f complement, we will get f. Suppose this is the example. Simplify f of ABCD is equal to sigma. How many variables are there? 4 variables. Sigma 0, 1, 2, 5, 8, 9 and 10. Combining the squares with ones gives the simplified function in sum of products form. F is equal to B bar D, B bar C bar plus A bar C bar D. Now what we have to do? We have to combine zeros now. By combining zeros, what we are getting? We are getting f complement, f dash. F dash is equal to AB plus CD plus BD bar. See this example, see this table. Now ones are mapped. For the empty squares, in empty squares we are filling with zeros and we are mapping those zeros. By mapping those zeros, what we are getting? We are getting this expression. The expression, that expression is called f bar, f complement. F complement is equal to AB plus CD plus BD bar. AB plus CD plus BD bar. So this is the expression. So what we have to do? We have to apply. That is f complement. We have to get f. For that, what we have to do? We have to perform complement. Complement by using De Morgan's law or by taking dual and complementing each letter. So we are using, if we use De Morgan's law or any other method, we will get this expression. That expression is equal to f is equal to a bar plus b bar into c bar plus d bar into b bar plus d. This is product of sum simplified expression. Now this is gate level implementation. So we are having sum of products expression and product of sums expression. So the gate level implementation of sum of products expression and its product of sums expressions are, see, sum of product expression f is equal to b bar d bar plus b bar c bar plus a bar c bar d. For that, what we need? For these three terms, we need 3 AND gates. For combining, we need 1 OR gate. 3 AND gates and 1 OR gate. For this expression, for this product of sums expression, f is equal to a bar plus b bar plus c bar plus d bar plus b bar plus d. For this, we need 3 OR gates and 1 AND gate. This is gate level implementation for sum of products and product of sums expressions. Now, see, product of sum simplification. And the procedure for obtaining the product of sum simplification when the function is originally expressed in sum of minterms or minterms canonical form. The procedure also valid when the function is originally expressed in the product of max terms canonical form. So consider this example. This example, first you go through this truth table. Here 3 variables are there. One output f. The output value is 1. F is 1 in 4 situations, in 4 cases. That is 0, 0, 1, 0, 1, 1, 1, 0, 0 and 1, 1, 0. That is 1, 3, 4, 6. In sum of minterms, the function is expressed as f of xyz is equal to sigma 1, 3, 4, 6. In product of max terms, it is expressed as, that is, in sum of products 1, product of sums 0, f of xyz is equal to pi of 0 to phi 7. Right. So, what we are doing, this is one way of expressing, this is another way of expressing, simplifying product of sums. And now we are going to discuss about don't care conditions. What are these don't care conditions? What is the need of these don't care conditions? Real circuits don't always need to have an output defined for every possible input. No need of all possible outputs. For example, you consider this one. Some calculated displays consist of 7 segment LEDs. We know that 7 segment LED. For any LED light, okay, for number, we are using 7 segment LED. These LEDs can display 2 to the power of 7 minus 1 patterns, but only 10 of them we are using. 0 to 9 only we are using, but it gives 2 to the power of 7 minus 1 patterns. That is, all those things, remaining things are not required. If a circuit is designed so that a particular set of inputs can never happen, we call this set of inputs as don't care conditions. And these are all very helpful for us in K-map circuit simplification. Now we will discuss in detail about how to handle this don't care conditions. In a K-map, don't care condition is identified by an X symbol. We are denoting it as X symbol in the cell of the minterms for the don't care inputs as shown below. In performing the simplification, we are free to include or ignore the X when creating our groups. So here the expression is, simplify this Boolean expression, f of wxyz is equal to sigma 1, 3, 7, 11, 15. So 1, 3, 7. How many terms are there? 5 terms. 5 terms, 5 ones we will get. And having don't care conditions, D of don't care conditions are represented like this. D of wxyz is equal to sigma 0 to 5. How many don't care conditions are there? 3. So how many we are plotting? 4. That is 0, 2, 5 and 8 also. Okay, here we have to add 8 also. So what we are having for some of products we are using ones, and for don't cares we map X into. Okay. In one group in the K-map below we have the function. So if you consider this one, we are considering 0 and 2 don't care conditions. So while grouping we have plotted like this, and we got this expression, the f of wxyz is equal to w bar y bar plus yz. Suppose if we group in another way, this is another way of grouping. F of wxyz is equal to w bar z plus y plus yz. So here what we are getting, we are getting two different expressions. That is w bar y bar plus yz, and this is w bar z plus yz. However, the values for which they differ are the inputs for which we have don't care conditions. So we need not worry about this. Okay, we can group as per our convenience. So more about don't care conditions. In practice, some combinations are not specified as ones or zeros. We are unable to specify, or there is no need to specify ones and zeros. Those combinations are considered as don't cares. 4-bit binary codes has 6 unused combinations. That means we have 0 to 15. In that 0 to 9 only we are using. So we are those 6 combinations from 10 to 15 are unused combinations. Those are considered as don't care conditions in simplification of Boolean expressions. Functions having unspecified outputs are called incompletely specified functions. We don't care the unspecified minterms, and these minterms are called don't care conditions. They can be used for minimization, and they are indicated as X in the map, and they can be assumed as ones or zeros to have best simplification. This is about don't care conditions. And NAND and NOR implementation. Here, NAND and NOR gates are called universal gates. Why we are calling them as universal gates? By using these NAND gate or NOR gate, we can implement any gate, either it is AND gate, OR gate, NOT gate, basic gates. We can develop any other gate, XOR gate, XNOR gate, like that. We can develop any gate by using these two gates. That's why we are calling these gates as universal gates. These NAND and NOR gates are generally used for circuit design, easier to fabricate. We can implement basic gates by using these NAND and NOR gates. Other functions also can be generated by using these NAND and NOR gates. And the rules have been developed to convert functions to NAND and NOR only implementations. This is NAND gate. This is NAND gate is called universal gates because we can implement any gate. So this is the implementation of NOT gate. First NOT gate by using NAND gate, AND gate by using NAND gate, and OR gate by using NAND gate. For NOT gate implementation, we are using A, same A we are using, okay, that is A, another, there are two inputs for this NAND gate, A and again A. A into A becomes A only, and not A bar. That is, if we give A, we are getting A bar, that is called NOT gate. Here in second one, we are developing AND gate by using NAND gate. For this, we have two inputs. For first AND gate, first NAND gate, and same input is given to another NAND gate also. So by that we are getting AB, that is similar to AND gate. And next one is OR gate. What is the output for OR gate? A plus B. We have to. Okay, we have to get A plus B. Here also we are using two NAND gates. For first NAND gate we are giving A and A again, and for second NAND gate we are giving B and B also. So we will get from first NAND gate we will get A bar, and for second NAND gate we will get B bar. We are giving these two A bar and B bar to NAND gate. We will get A bar into B bar whole bar, that is equal to A plus B. This is nothing but OR gate. This is NAND implementation. And two graphic symbols for NAND is, this is AND invert NAND gate and invert OR NAND gate. So we can use both ways. AND invert NAND gates are represented by using AND invert or invert OR also. What is AND invert? Here there are three inputs, X, Y, Z, and a bubble is there, that is as usual NAND gate, X, Y, Z whole complement. Whereas in invert OR, first we will place invert X invert, Y invert, Z invert, and OR gate, that is equal to X bar plus Y bar plus Z bar, that is equal to X, Y, Z whole bar. This is graphic symbols. And two level implementation. Have the function in sum of product form, put bubbles or inverters to have two different representation of NAND gate, either AND invert or invert OR. So example, implement this F is equal to AB plus CD by using NAND gates. As usual, to implement this circuit, we need, for AB we need AND gate, for CD we need AND gate, and for plus we need OR gate. So two AND gates and one OR gate is required. And we are implementing this one by using AND invert and OR invert. AND invert OR. So the diagram be NAND gate, and that is invert OR gate. That is implementation of that expression. And here in second diagram, that is C diagram, we have used three NAND gates to implement that expression F is equal to AB plus CD. So now implement this F of XYZ is equal to sigma 1, 2, 3, 4, 5 with only NAND gates. We have to implement by using only NAND gates. So what is the procedure? Same. F of XYZ is equal to sigma 1, 2, 3, 4, 5, 7. So we have to, by using K map, we have to minimize the expression first. So what is the method we have to follow? This is 3 variable K map. How many squares will be there? 8 squares. by using map simplification, we will get f is equal to x y bar plus x bar y plus z. So we are implementing in two ways. X y bar we are using directly to NAND gate, x bar y another NAND gate, and z NOT gate we are giving it to invert OR, that is f. Or we are using all NAND gates x y bar, x bar y and z bar, we will get this required expression. This is about implementation of NAND gates. And another thing is that this is multi-level NAND circuits. Here multi-level NAND circuits. Suppose one expression is given, f is equal to a into cd plus b plus bc bar. Okay, we can, by using AND and OR gates, we can implement this. By using NAND gates, we can implement this one like c bar d, that is like this. Okay, how many NAND gates are there? 2 NAND gates, total 3 NAND gates and 2 OR inverts, invert ORs. So this is the multi-level NAND circuit. Now this is NOR gate, NOR implementation. So we know NAND gate and NOR gates are called universal gates. So why we are calling it as universal gates? By using these gates we can implement any logic circuit. So now we are discussing about NOR gate. By using NOR gate, how to implement, how to develop NOT gate, AND gate and OR gate. So in the first one we have one NOR gate. The inputs of that NOR gate is A only and again A plus A. We are getting A plus A whole bar, that is equal to A bar only. Now for implementing A AND gate, we need 3 NOR gates, and for implementing OR gate we need 2 NOR gates. So this is the implementation of basic gates by using NOR gates. Now just like this NAND gate, we have 2 symbols for NOR gate. One is OR invert and another one is invert AND. Invert AND and OR invert. OR gate with invert, that is called NOR, it gives NOR gate. This is as usual NOR gate only. And in the form of AND, invert and AND to implement NOR gate. And here is the expression f is equal to, we implement this expression, f is equal to a plus b into c plus d into e. So by using these NOR gates and invert AND gates, we can implement this diagram. And NOR implementation, this is another diagram by using invert and NOR gates. So finally we are going to discuss about XOR gate. What is this XOR gate? X XOR y is equal to x y bar plus x bar y. 1 if only x is 1, or 1 if only y is 1. So that is the truth table. What is the truth table for this XOR gate? 0 0 0 0 1 1 1 0 1 1 1 0 1. So what about the XOR gate? X exclusive or y whole complement is equal to x NOR. That is equal to, the expression for that is x y plus x bar y bar, and this XOR gate is also called equivalence gate. What is why we are calling it as equivalence gate? If the values of x and y are same, then only the output of XOR gate is 1. What about XOR gate? In XOR gate, the x and y values are different only, we are getting 1. Whereas in XOR gate, if the values of x and y are same, then only we are getting 1. And some identities of XOR are x exclusive or 0 is equal to x, x exclusive or 1 is equal to x bar. This is identity of XOR. X exclusive or 1 is equal to x bar, and x exclusive or x is equal to 0, x exclusive or x bar is equal to 1, and x exclusive or y bar is equal to x bar exclusive or, that is equal to x exclusive or y whole bar. This is about XOR gate, and with this we have completed this session. In this session we discussed about first one, map simplification. Map simplification means this is gate level minimization. In this gate level minimization, we used this map simplification method. Map means here Karnaugh map, and two variable we discussed about two variable Karnaugh map, three variable Karnaugh map, four variable Karnaugh map, and we practiced some examples on two variable Karnaugh map, three variable and four variable Karnaugh map, and we discussed about five variable Karnaugh map also. And then we discussed about don't care conditions, how to use don't care conditions while minimizing the circuits, and NAND and NOR implementation. NAND and NOR gates are called universal gates. How to implement other logic circuits by using NAND and NOR gates we discussed, and finally we discussed about XOR gate.